All right, so I had just started recording this video, and then my dog came and started barking at me, and so I had to stop the video, go kind of put him away, and now I'm returning to this. So what I'm going to do, since I already worked through this first example, I'm going to talk you through it, just using the work that I already did. Before we do that, what are we talking about with this support class? The focus today is on solving polynomial equations, something you spend a lot of time doing in Algebra 1 and Algebra 2. The goal of studying this here is to help us with section 9.5 in the parent class, where we talk about solving trigonometric equations. Now, even though those are different types of equations, they do have a lot of similarity sometimes to polynomial equations, and so the techniques that we learn in algebra end up being useful there. So this is kind of just a review of that specific topic. Let's get into it. I wanted to start by solving this equation here. X squared minus 4x minus 60 equals 0. The way I was going about this is by taking a look at the quadratic equation on this side, the quadratic expression on this side, and trying to factor it. Now, I did my diamond method over here and found that it factored to x minus 10 times x plus 6. We did a lot of factoring in a previous support class, so hopefully that's something that you're remembering how to do. Now, there's a key thing about the way this is represented here. I have a product of two factors on this left-hand side, and I have a 0 on the right-hand side. That allows us to use something that we learn in algebra called the zero product property, which says if I have a product of two things that are in that product is equal to 0, then that must mean that either one of those was equal to 0. Either x minus 10 was equal to 0 or x plus 6 was equal to 0. That's the only way that a product can come out to 0. So we think about what x would be in either of those cases. If x minus 10 equals 0, then x is equal to 10. If x plus 6 equals 0, then x is equal to negative 6. Then as a final step, as we oftentimes do with these sorts of equations, I represent my solution or my solutions in the form of a set containing the numbers 10 and negative 6. This is very typically how we write our solutions. Okay, so that's one example of solving a polynomial equation. And the key here was to use that zero product property. We're going to try and keep using that when we can. So let's look at another example. I'd like to solve this equation. 10x squared minus 7x equals 2 minus 5x squared. Okay. Now, this looks different from the previous one, but it involves quadratic terms. It involves x squareds, so I'm suspecting that we can use a similar technique. But where this equation was better suited for the technique that we used than this one was the fact that it had a 0 here. Remember that 0 is an important ingredient for using the zero product property. That's not as big of a problem as it seems, because I can always get a 0 on one side of an equation by subtracting everything over to the other side. So for example, if I subtract 2 to the left-hand side, I'll have a minus 2 here. If I take this minus 5x squared and add it to both sides, it'll combine with this 10x squared, giving me 15x squared. And I end up with this, 15x squared minus 7x minus 2 equals 0. So if we don't already have a 0 on one side of our equation, your first goal is generally going to be to put one there, and you can always do that. Now, we have a quadratic on our left-hand side, and this can be factored. The difference between this quadratic and the previous example is that the leading coefficient is no longer a 1, it's a 15. And that's fine, we know what to do with that. We can go to our diamond method, and in this case, we take that leading coefficient and multiply it to our constant term, just like we did when we talked about factoring. 15 times negative 2 is negative 30. Excuse me. Then, what we want to do is take our x terms coefficient, the negative 7, and put that down here. Now, what are we looking for? Two numbers that multiply to negative 30 but add up to negative 7. Once again, because we're multiplying to a negative number, one of those terms should be negative, the other should be positive. And after a little bit of work, you can probably determine that negative 10 and positive 3 would do the job. They multiply to negative 30, but they add up to negative 7. Now this is where the method starts to look a little different than the previous example. We don't just stick with these numbers, we create fractions out of them. And the denominator of both of these fractions will be the same number. It's whatever my leading coefficient was, 15 in this case. Then we simplify these fractions as much as possible. Negative 10 fifteenths becomes negative 2 thirds, and 3 fifteenths becomes 1 fifth. Now, if you remember, the goal here is to read these from the bottom up to show me how to factor this. I think of this denominator as having an x in it, 3x minus 2. 3x minus 2 times 5x plus 1, because that's positive. 5x plus 1. And we set that equal to 0. Once again, because we have a product of two things equal to 0, I can separate those out and say 3x minus 2 equals 0, or 5x plus 1 equals 0. And now we're just solving each of those equations separately, both of which are very straightforward. They're just two-step linear equations. This one gives me x equals 2 thirds. This one gives me x equals negative 1 fifth. Okay, so my solutions are 2 thirds, negative 1 fifth. Not too bad. All right, let's move on to another example. This one is going to be the following. Solve x to the fifth equals 16x. Oftentimes, when somebody is presented with an equation like this, their first instinct is to divide both sides by x. And you definitely do not want to do that. The reason for that is because by dividing both sides by x, you are assuming that x is not equal to 0. But we have no reason to believe that x can't equal 0. In fact, if I plug a 0 in for x, I can see right away that's definitely a solution to this, because both sides become 0. But if x is equal to 0, you can't divide by it, because you're not allowed to divide by 0, right? So you don't want to divide both sides by x, because it's possible that you're dividing by 0 in the process, and you will lose a solution by doing that. Instead, we want to follow the exact same approach as before. Subtract everything over so that we have a 0 on one side. Now I have a GCF, a common factor that I can take out. I can pull an x out of this. It becomes x times x to the fourth minus 16. Okay? Now from our factoring unit that we did, our topic on factoring, we should recognize this thing in parentheses as a difference of two squares. So that being said, let's try and factor this further. X times, this should look like x squared plus, what's the square root of 16? That would be 4. X squared minus 4 equals 0. Okay? Now this is a sum of squares. I cannot factor that any further. But x squared minus 4 is a difference of two squares, and I can definitely factor that further. X plus 2, x minus 2, and we have that equal to 0. Okay? Now, the work that we've... sorry, that's the wrong page. The work that we've been doing from the stage where everything is factored is we were writing each of our factors and setting them equal to 0 and then solving. But once you've done this enough times, we typically skip the step of writing this out. With practice, you eventually get down to this step and you're able to look at this and say, okay, 2 thirds. Okay, negative 1 fifth. So you should be able to start seeing the answer without having to write that out every time. And because there's several factors here, that's what I'm going to do. X, I would set that equal to 0. X squared plus 4, I would set that equal to 0. X plus 2, I would set that equal to 0. And x minus 2, I'd set that equal to 0. But it's a lot of work for something that's not very difficult to think through. If x is equal to 0, that means 0 is one of my solutions. I'm going to skip this guy for a second. X plus 2, if that's equal to 0, then x would have to equal negative 2. If x minus 2 is equal to 0, then x is equal to positive 2. Okay? Now the issue with this guy right here, let me go off to the side, and that's the one factor that I will set equal to 0. If I try to solve that, I know that I can't factor it any further, so maybe let's try subtracting 4 from both sides. X squared is equal to negative 4. You know that you can solve things like this by taking square roots of both sides. X is equal to plus or minus the square root of negative 4, except you're not supposed to be able to take square roots of negative numbers. In intermediate algebra, you learn that actually you can take square roots of negative numbers. You get plus or minus 2i, in this case, where I is the imaginary constant. Now, we're going to be working with complex numbers, imaginary numbers, in Chapter 10 of the parent course. So we are considering imaginary numbers as valid solutions here. Plus or minus 2i technically is okay to write in your solution set. If you're a little fuzzy on imaginary numbers, don't worry too much about it, because we are going to review that in the support class before we get to that section in the parent class. But this is just to remind you that those things do end up being solutions to equations like this. Okay? I want to do one last example. Solve 2x squared minus x plus 5 equals 0. Okay? Doesn't look that difficult. I mean, it looks very similar to the, first or second example that we did. The problem is that the left-hand side does not factor. You can try all you want, and you're going to find that this does not factor down to anything that we can find. So that technique is not going to work here. But we do have a technique that always works, and that's by using the quadratic formula. So if you need a reminder, the quadratic formula says that if you have a quadratic equation of the form ax squared plus bx plus c equals 0, then x will equal negative b plus or minus the square root of b squared minus 4ac all over 2a. You learn that in Algebra 1, and you use it a bunch in Algebra 1 and Algebra 2. And it's really something you should have memorized just from that. But I know a lot of people remember this to the tune of a song or a poem or something like that. And you can look those up on YouTube if you want to find a good mnemonic device for remembering this. But this is what I'm going to use. So what is A, B, and C? Or what are A, B, and C in this case? A is my leading coefficient, so A is 2. B is the term, the coefficient on my x term, which would be a negative 1. And C is my constant term, C equals 5. So I'm just going to plug all of that into my quadratic formula. X is equal to negative b, which would actually be positive 1 in this case, plus or minus the square root of b squared, negative 1 squared, minus 4ac, 4 times 2 times 5. Okay, all over 2a, 2 times 2. And now it's arithmetic. We're just simplifying this down. This is equal to 1 plus or minus the square root. So negative 1 squared would be 1. 4 times 2 times 5, that's going to be 40. So minus 40 all over 4. This is equal to 1 plus or minus the square root of negative 39 all over 4. And then once again, we're dealing with a negative under that radical. And like we said, in Algebra 1, you would be told to look at this and say no solutions or no real solutions. But now that we know what complex numbers are, imaginary numbers, we can do something with this. This is the same thing as 1 plus or minus I times the square root of 39 over 4. And like I said, again, we're going to do some review of imaginary numbers and complex numbers a little later in the support course. So if you can't remember why that negative comes out like an I, it's okay. We'll review that, and you'll have a chance to make more sense of that later on down the road. But in this case, I'm going to just let my answer look like this. I don't really need to put this one in set form. Okay, that should give you a good mix of examples to prepare you for the assignment for this week, which is really just solving a bunch of equations of this type. So that's it.